So if we don't have an odd power of the secant, we hope to have an odd power of the tangent. And the goal is to end up the integrand with secant times tangent times d theta, as we know that the antiderivative of the secant times the tangent is the secant. So here we have odd power of tangent. So again, we're looking at m. So m equals 2k plus 1, and k can start at 1. Okay. So again, what we want to factor, we want to factor both secant and tangent. So we want to factor this product because we want to get secant times tangent d theta. So we need to factor a product of these two. So let's devise the this situation. The integral I tangent theta to the n power secant to the n, and if the m is an even number, an odd number, take it back, then we have 2k plus 1 secant. And I want to have the product secant times tangent, so I need to take 1 from each. So I'll have tangent theta to the 2k times tangent theta, and then the secant, I'm going to borrow 1, so it would be n minus 1 times the secant, and then d theta. So here is what I need, the 3 component. As before, since now I have an even power of the tangent, 2k, after borrowing 1, I can write it as tangent squared raised to the k power, and the secant n raised to the power of n minus 1, and here I have the secant tangent combination. The substitution as before, the tangent. Well, if you think about the substitution before, if the tangent, let's do a little bit recall here, okay? Let's do a side note, because for some of you it won't be that trivial, but you know the identity. We're going to use the following. Use if the secant squared equals 1 plus the tangent squared, well, then the tangent squared can be replaced by the secant squared minus 1. Okay? So this is going to be replaced. So I equal, instead of the tangent squared, I'm going to have the secant squared right there. So secant squared minus 1. So we have secant squared theta minus 1 raised to the power of k times the secant raised to the power of n minus 1, and plus the differential secant theta tangent theta d theta. What we accomplish here, this is the derivative of the secant, and everything else is expressed in terms of the secant. So now we can perform the substitution, and the substitution will be u equal the secant, and therefore du equals secant tangent d theta. And therefore, after the substitution, I equal the integral, and here we have u squared minus 1 to the k power, u to the n minus 1 du. And again, this is the recipe for those with exceptional memory. Here's an example. This will be example 6. We want to evaluate the integral of tangent to the 5th times secant to the 7th. Okay. Now, if you want to use the recipe, then you need to recognize that n equals 5, therefore k equals 2, and n equals 7. Okay, but as before, I go with Byron here, who said, no, let's go ahead and develop it. Actually, in my notes, I used the recipe, but I want to emphasize the other method. So let's do this. Let's write the integral of tangent to the 5th secant. You'll see that it's fairly simple to forgo the recipe and say, okay, let's break it down. I know that I need to extract one secant and one tangent, right? So it will be tangent to the 4th, and it will be secant to the 6th, and then I have the secant multiplied by the tangent. So it's not that bad. The next thing I need to do is write tangent. Now I have the tangent to the even power, write it as tangent squared raised to another power, so I can replace that. So we'll have the integral of tangent squared secant to the 6th secant times the tangent. My 5-minute warning. Substitute this one with the secant squared minus 1. Squared again. And secant to the 6th. And here's the secant times tangent. And now we substitute. U equals the secant. And therefore du equal secant times tangent d theta, and I, the integral, will be u squared minus 1, all of it squared, u to the 6th du. Okay? So again, this part won't be necessary if you remember this formula and you do the necessary adjustment. You plug in k equals 2 and n equals 7, and you can see that u squared minus 1 raised to the power of k raised to the power of 2, and u to the 7 minus 1 is 6. So you can save yourself, but I think it will be easier to remember the concept rather than the formula. So let's clear the parentheses here and finish this up. So first we need to use the binomial expansion, so we'll use u to the 4th minus 2u squared minus plus 1 times u to the 6th du, and now clear everything, so you get u to the 10th minus 2u to the 8th plus u to the 6th du, and now the antiderivatives. 1 over 11 u to the 11 minus 2 over 9 u to the 9 plus 1/7 u to the 7th plus c. And finally, go ahead and back substitute or replace the secant, u with the secant, and you get 1 over 11 secant to the 11th power minus 2 over 9 secant to the 9th power plus 1 over 7 secant to the 7th power plus c. And believe me or believe it, that if you take the derivative of the result, you'll be able to recover. It won't be easy, mind you, because you need to do your trigonometric identities, but the derivative of this equals the integrand, tangent to the 5th times secant to the 7th. But probably it will be probably it will be even harder to check in this case. I think this is a good time to stop. What happened next is the following. What happens if we don't have any of these tools available to us? For instance, we don't have the tangent being even or the secant being odd.